Okay, today we're going to be continuing Chapter 8 and actually finishing Chapter 8 on hypothesis testing. So our studies today, we're going to be focusing on Section 8.4, where we're going to be learning about testing a claim that involves a standard deviation or a variance. So far we've looked at proportion, mean, and today we'll do standard deviation and variance. So here's our flow chart. We've covered the proportion branch. We've covered the two mean types. So now we're going to be over here. And as you can see, most of the steps are the same. Identify the claim, identify the values in the problem. It's going to be standard deviation or variance. So you set it up using your null hypothesis as one of these, depending on which one it is. You'll have your requirements, your test statistic, calculate your p-value, get your statistical conclusion, and then your non-technical conclusion. So it has the same steps as what we've been doing before. Okay, so this one we're going to be looking at methods for conducting a formal hypothesis test of a claim that's made about either the standard deviation or the variance. And this is actually going to use the chi-square distribution, just like our confidence intervals did when the confidence interval was used to estimate a standard deviation or population variance. Okay. All right, so just make sure that you're familiar with these, which by this point in the course you definitely should be. N is your sample size, S is the sample standard deviation, sigma is the population standard deviation, S squared is the sample variance, and sigma squared is the population variance. Okay, just like when we were doing the confidence intervals involving the standard deviation and variance, the requirements are going to be the same. So the requirements are that it is a simple random sample, and that it comes from a population that has a normal distribution. And as we said before, this is a strict requirement. We can't get around this by using a large sample. We have to know that the population is normally distributed. Okay, the test statistic that we're going to use is chi-squared, is n minus 1 s squared over sigma squared. And we typically want to round this to 3 decimal places, and we're primarily going to be doing the p-value method instead of the critical values. So just to recap from when we looked at chi-squared before, chi-square distribution is skewed to the right. All the values are non-negative, meaning they go from 0 to infinity, but we don't have any negatives here. And as I said, it's not symmetrical. We do have degrees of freedom for each sample size. So our degree of freedom is n minus 1. So every different sample has a different degree of freedom and therefore a different graph associated with it. All right, so I want to take a look at this data set here. Listed below are the heights for the simple random sample of female supermodels. We want to use a 0.05 significance level. So here is our alpha to test the claim. So here's our claim that supermodels have heights with a standard deviation that is less than 7.5 centimeters for the population of women. Does it appear that heights of supermodels vary less than heights of women from the population? Okay, so we have our claim here, we have our alpha, we have our data set. So anytime you have a data set, you want to enter this in your L1 and go ahead and get your statistic from it by doing your one variable stats. And keep that in there in your calculator because we will need that for other things as well. Okay, so like I said, here's your claim, and that claim is a claim about the standard deviation. So that tells us it is going to be an example where we would use the method for hypothesis testing about the standard deviation. We look at our requirement check. The first one is a simple random sample. They tell us that that is the case in this one. The other is that it is from a population that's normally distributed. We're not told that, but if you do your normal quantile plot, and just as a reminder, that's the 6th graph on your stat plot menu. If you do your normal quantile plot, it doesn't line up perfectly, but basically it is close enough that we can go ahead with this. So identifying our values, we need the S. So the S is here. You are not going to be using this value, so do not use that value. Okay. So we've got our S, our N, our degree of freedom is 1 less than the sample size. Significance level was given, and the the sigma that you want to use is the one from the claim. not the one listed here. So many times I've seen people write down this one here and use it in the problem, and you have to get this from your claim. Okay, so we need to set up our null and our alternative hypothesis. So we know that it's a claim about the standard deviation. So we need to use the parameter for sigma for standard deviation. The null hypothesis will always be our equals one. And if we go back and look at our claim statement, the claim is that supermodels have heights with a standard deviation that is less than 7.5. So that's what we want to use when we set this up. So less than 7.5 for our alternative hypothesis there. And this is our original claim, so keep in mind that our original claim is in the alternative hypothesis. The test statistic that we're going to calculate is chi-squared equals n minus 1 s squared over sigma squared. So obviously n is 16 minus 1. This is coming from your one variable stats. And this is coming from the value in your claim. Be sure that you square both of those. That's another thing that people tend to not do. So be sure you keep track of whether what those values are. If your claim happens to be a claim about the variance, then that number would already be squared and you would not need to square it again. So really keep track of whether you're talking about standard deviation or variance within your problems. Okay, we want to find our p-value. So just like you use a normal CDF when you have a Z test statistic, use a t-CDF when you have a t-test statistic. You're going to use a chi-squared CDF when you have a chi-squared test statistic. Okay, so the chi-squared CDF is on the same list with the normal CDF and the t-CDF. You'll go down to number 8, you'll see your chi-squared CDF. So we're going to put the test statistic on our graph, and it's a less than problem, so we're going to shade to the left. So we're going to do our chi-squared CDF from 0. Remember, the chi-squared distribution does not go below 0. So instead of doing negative E99, we're going to do 0 here. 0, our test statistic, and then finally our degree of freedom. We get this as our p-value, which is practically 0. One good thing is if you happen to forget and put in negative E99, you're still going to get the right answer. So don't worry too much about that. Okay, so if we wanted to do this on StatCrunch, what we could do is we would enter our data here in the first column. We'll go to Stat and Variance Stats, one sample, and then since we have our data, we're going to choose With Data. We'll go in and we'll choose our variable. For our hypothesis test, we're going to put in 56.25, and this was less than. And we're going to compute. So one reason we did 56.25 is because this only allows us to put the variance in. And so our variance, if we look back on if we look back here, our variance is 7.5. So if we square our standard deviation is 7.5. If we square 7.5, we get 56.25. And so that's why I'm entering that in for the StatCrunch. Okay, so put that in for the StatCrunch because it only gives me the option of the variance, and then I'm going to get my same test statistic and p-value that I'll be using there. Okay, as far as our conclusions go, since our p-value was very small, it was less than our 0.01, which was our alpha, we're going to choose to reject the null hypothesis. And if we look, we had sigma equals 7.5, and we had sigma is less than 7.5. So this was our claim here. We had identified that to be the claim. So our claim is that female supermodels have heights with a standard deviation that's less than 7.5. Okay, and we said that we're going to reject our null hypothesis. So we're rejecting the null hypothesis in support of this new claim that we have here. So that's why we would say there is sufficient evidence to support the claim that female supermodels have heights with a standard deviation that's less than 7.5 centimeters for the population of women. So because 7.5 is considered to be the standard deviation for women, and because we just proved that that supermodels have standard deviations that are less than that, because they're less than that, then it appears that there is less variation in the heights of women that are supermodels than in the general population. Okay, here's another one for us to try. If you feel comfortable, certainly pause it and try the video or try the problem. If not, then just stay with me and follow along. So a cigarette manufacturer wishes to test the claim. So here's our claim that the variance of the nicotine content of its cigarettes is 0.644. Nicotine content is measured in milligrams and assume that it's normally distributed. So that's important. A sample of 20 cigarettes, so that's our N, has a standard deviation of 1 milligram. Okay, so this is our S. It's an S because it's coming from the 20 cigarettes that were sampled. It's not coming from the population. Okay, at a 0.05, so this is our alpha significance level, is there enough evidence to reject the manufacturer's claim? Okay, so we've identified the claim. The claim is about the variance, so we're going to be doing the type confidence interval that has, or type hypothesis test that has, uses the chi-square distribution. So like we said, this is going to be the variance type. And we know that our values are sigma squared, which is our variance, is given to us as 0.644 milligrams. The S is also given to us in the problem. That's going to be 1 milligram. Our sample size, we were told, is 20, and our alpha is 0.05. So we want to make sure that we fulfill our requirements. So our requirements are that it's a simple random sample and that it is normally distributed. If you recall, we were told it was normally distributed, so we're good with that. We set up our null and our alternative hypothesis. Because our claim was a claim about the variance, then this time I'm going to actually state it with the variance. So it's going to be the population variance equals the value here, which is 0.644. Okay, and again, looking at the claim is 0.644, so there's no indication of direction. So we are going to do does not equal for this. Okay, so we're ready to find our test statistic. So our test statistic is chi-squared equals n minus 1 s squared over sigma squared. So my n minus 1, n is 20, so 20 minus 1. S is 1. We'll divide that by sigma squared. And if you notice, this is what I was saying earlier about be sure you keep track of whether something's squared or not. This is actually already squared, so I don't need to square this again. So I'm going to leave it just as it is. So when I put that in, I get 29.503. Okay, so we need to find our p-value. So we've got 29.503. On a two-tailed test, and it's chi-squared, it's a little difficult to know whether to put our test statistic on the right or on the left. For now, I'm going to go ahead and tell you to put it on the right so you can see how it works, and then I'm going to show you how we would know if we put it on the wrong side. All right, so we want to find this, so we're going to do chi-squared CDF from 29.503 to infinity. Our degree of freedom is 19. So we get 0.0584. Okay, so that's this area here, but it's a two-tailed test, so we also have an identical area over here. So we need to make sure that we times that by 2 before we declare that it's our p-value. So this will be 0.11 0.68. So that is my p-value. Okay, then we want to compare the p-value to the alpha. So the p-value is 0.1168. My alpha is 0.05, so this is a larger value. So when the p-value is larger than the significance level, we are going to fail to reject the null hypothesis. That is going to be our statistical conclusion. Okay, if we look up here, our claim statement, again, we need to determine which one of these is our claim statement. So if I look at this claim statement, it turns out that this is actually the one that is the claim statement. This is the one that in symbols says the same thing that the claim said in words. Okay. So if I have decided that I'm going to fail to reject the null hypothesis, if I fail to reject it, that's the same thing as saying do not reject it. So what we'll say is there is not evidence to warrant rejection of the claim because the claim is our null hypothesis. And that would be our statement for this one here. It's written out here, there is not sufficient evidence to warrant rejection of the claim that the variance of nicotine content of its cigarettes is 0.644 milligrams. Okay, I said that sometimes it's difficult to know sometimes it's difficult to know which side to put it on when it's a two-tailed test. So with the t-distribution and the normal distribution, if your test statistic is negative, it goes on the left. If it's positive, it goes on the right. But everything is positive with the chi-squared. So when it's a two-tailed test, it's difficult to know which tail to use. So what we're going to do is I want to show you here, what if we were to have put it on the wrong side? So if you remember, we put it on the right side and we found the right tail. If we put it on the left side, then when we go to find this area, we'll do chi-squared CDF from 0 to our test statistic with 19 degrees of freedom, and we're going to get this value here. When I double that, then I get this. That can never be a p-value because p-values can't be greater than 1. It's not going to be 1.883. So that's an indication that it's on the wrong side and that you need to move it to the other side. So watch your p-values, make sure they're not more than 1. The only case you have to worry about this is the two-tailed test for chi-squared. Okay, no other situations do you have to worry about it other than the two-tailed test for chi-squared. Okay, one way you can kind of use as a guide here, this one we said our degree of freedom was 19, so we're going to be focusing on this row here. And our test statistic on this one was 29.503. So keep that in mind. If I look down here for 19 degrees of freedom, 29.503 falls right in here, okay? And that's on the right side of the chi-square distribution. This would be on the left side. So if this value had fallen somewhere over here, then I would want to put it on the left side of my graph. But because it's fallen over here, I'll put it on the right side of my graph. So that's another way to kind of use some guidance to figure out which side of the graph to put it on. Okay, so here's another one. I would like for you to try this one and then check your answers. Okay, here's our next problem. Tests in a statistics class have scores with a standard deviation equal to 14.1. One of the professor's last tests had 27 test scores with a standard deviation of 9.3. Use a 0.01 significance level to test the claim that this class has less variation than other past classes. Okay, so a couple things going on here. The claim is that this class has less variation than other past classes. So less variation. If you remember, we have different measures of variation. Range is a measure of variation. Standard deviation and variance are measures of variation. Since we are talking here about standard deviation, then we're going to use the measure of standard deviation when we talk about their claim. So the claim that the class has less standard deviation than other past classes. So we need to come up with a value here. And if you read in the past, classes had a standard deviation of 14.1. So that's the value that we're going to be using there. We also know that this is going to be our alpha. This is going to be our N. This is our S because it's the standard deviation coming from our sample of 27. So it would be an S and not a sigma. And this is actually going to be our sigma because it's in the claim. It's the value that we're using in the claim. Okay, so when we go to start setting this up, we know that just going to get everything out here in front of us. N is 27, alpha is 0.01, S is 9.3. We know that sigma coming from the claim is 14.1. So if we do our requirement check, we've got simple random sample, and if we look, we're told that assume that it's normally distributed. So we're going to be able to check that off as well. So we're ready to set up our null and our alternative hypothesis. This one is about standard deviation, so we're going to use the sigma. The value that from our claim is that it's less than the other past classes, which had a standard deviation of 14.1. So that's the value we're going to use. And less than indicates what we'll use for our alternative. So we'll have less than 14.1 for the alternative. So this is going to be our claim here in the alternative hypothesis. So we're ready to calculate our test statistic. So we're going to have chi-squared is n minus 1 s squared over sigma squared. So n is 27. S we were told is 9.3. And sigma is 14.1. Okay, so if we put that in, we'll have 11.311. All right, this one is a left-tailed test where we don't have to worry about deciding which tail to put it in. We're going to be finding our left tail. So this is going to be 11.311, and we're going to be finding this. So we're going to do chi-squared CDF. Remember, this starts at 0, so it's going to be 0 to 11.311 with 26 degrees of freedom. So that's going to be 0.0056. And that is my p-value. It's a one-tailed test, so there's no need to double this. Okay, if I want to compare the p-value and my alpha, the p is 0.0056 and the alpha is 0.01. So the p-value is a smaller number than the alpha. So when the p-value is less than the alpha, we reject the null hypothesis. So here we're going to reject or throw out the null hypothesis in support or in favor of the alternative hypothesis. So our statement for this one would be, there is sufficient sample evidence to support the claim that the class has less variation than other past classes. Okay, so then the question, does a lower standard deviation suggest that this class is doing better? I would like for you to think about what your response to that would be for just a minute. Okay, so the answer to that is no. So even though we've shown that it does have a lower standard deviation, all that's saying is that there's less variation in the values, therefore the values are clustered more together. They may be all clustered in the failing category. We don't know where they're clustered. We just know that they're clustered a little tighter. Their variation is less. So it does not tell us that they're doing better. So that takes us to the end of this section.